Okay, so they record. So we'll go ahead and get started. If people pop in, I can pay attention and let them in. All right, so we just need to finish up a little bit of gases and then roll through solutions, and we'll finish up topic or unit 3, which everybody complains is the weirdest mishmash of unit. It's like where they put like these 2 things and these 3 things and whatever that didn't fit anywhere else. So it's a whole unit that doesn't make sense, which is why most teachers didn't actually follow their unit structure, but it's what we have for review. Okay, so deviation from the ideal gas law. So we know that the ideal gas law is ideal and not reality. This was always something that made more sense in multiple choice questions as opposed to free response. So it's unclear whether or not this is something that they would tie in to our new free response question format, although they could tie together a question about intermolecular forces and ideal gas law that they could then tie into larger things about structure and stuff like that, because intermolecular forces would impact your deviation from ideal behavior. So let's go through here. Pretty much an ideal gas, in theory, again, because it's ideal, it's not real, it means you have no volume, which we know is not true. It means you have no attraction between the particles of the gas, which we also know is not true, unless you are a noble gas, in which case you have very small amounts of attraction, you still have some, and that collisions are perfectly elastic. Fine. In reality, things have volume. So larger gases, right, larger gas particles are going to deviate more because they are larger. And real gases actually have attractive forces. So the more attraction they have, the more they will deviate from ideal. So those are the things to take away here. So if you have, the more attraction you have, the more deviation you will have, and the larger your gas particles are, the more deviation they will have. To overcome those things, you basically need to have the particles moving as fast as possible, because the faster they move, they will not have an opportunity to actually attract. And if you give them lots and lots of space to move around, then that volume that they have doesn't actually matter. So looking at this, so when a real gas is placed into a container at high pressure, why might the pressure of the gas be higher than what was predicted by the ideal gas law? So if you put them in a container at high pressure, what happens under high pressure?
The volume decreases.
All right, so the volume decreases. So you're squishing everything together into this tighter space of volume. So why might the pressure then be higher?
It's because they have more volume to take. I mean, they have, the gases themselves actually have volume, which
right. So you have to remember that pressure and volume are our inverse things. So if you squish them all together, you've actually reduced their amount of volume. So if you've reduced their volume, you've accidentally increased their pressure. Mm-hmm. Okay. So that's what you got to remember. I think we are more likely to see a question based on intermolecular forces here, but still, like, this sort of reasoning is helpful. So when a gas is cooled, why might the pressure of the real gas be lower than the pressure predicted? If you cool it down, what are the particles actually doing? Think through it.
There's the particles are slowing down.
All right, so the
pressure is decreasing.
So if the particles are slowing down, well, of course the pressure is going to decrease, but it's saying that the pressure decreases an extra amount than what you would expect. So if the particles are slowing down, what can happen between the particles?
They can attract.
They're spreading out.
They can attract. Carl nailed it. So if you slow them down, they can all of a sudden actually attract.
They have time to like actually connect to it.
Yes, they have time and opportunity to actually connect. And if they have time and opportunity to actually connect, then they will stick together more and have less opportunity to actually bang on the sides of the container. So remember, pressure is banging on the side of the container. So if they're all sticking together in the middle because they got all sticky because they're moving slow, then they're never even going to get to the sides of the container. Okay, so moving on to solutions. So all of the remaining topics for the most part deal with solutions and mixtures. So there are a couple of lab techniques here around molarity, as well as the molarity formula, that sort of thing. So molarity formula, we good on that? Do you know where that is actually on your formula sheet? Because it is actually on your formula sheet if you forget it. The other thing I would write on your formula sheet is that moles, right, equals molarity times liters, right? It's volume in liters. Because that is the primary way that you actually end up using the molarity formula. Is most of the time you use the molarity formula and a volume to get moles. So you can easily get moles that way by simply multiplying the molarity and the liters. So that would be a good thing to write in next to your molarity formula or somewhere on there. All right, everybody got a note of that? Clear it and move on?
Yes, yikes.
Yes, yikes, okay.
Because I dropped my phone and it was very loud.
Okay. Okay, so molarity is the main way we deal with concentration. Moles of solute dissolved in a total volume of solution. So you'll see most of the time they do use the big M when they're talking about lab situations, all that sort of stuff. Typically, the only time you are going to see moles per liter given is in kinetics problems. And I don't know why they do that, but in the text of problems, they'll use big M until you get to a kinetics problem, and then they like throwing mole per liter in there, which doesn't make any sense to me. Kinetics. It makes literally zero sense to me because it's harder to deal or to actually type it out mole/liter. But regardless, you do typically see that mole/liter in kinetics problems, the big M all the rest of the time in the text of questions. So we know all that. Solute, solvent, sure. So solution, remember, can be any mixture, solids, liquids, gases, although we do almost exclusively deal with it as solids dissolved into liquids. More molarity means you've got a higher concentration of solvent, right? That is all straight review from first year, easy enough. Okay, so now we want to get into a little bit of lab-based stuff. So in the lab-based stuff, there is some equipment, very few, that they expect you know what it is and how to use it properly and when to use it properly. So it all tends to be around solutions. So when you are making a solution, if you need small volumes of things, you are looking at a pipette most of the time, not a graduated cylinder. All right, so most of the time we are talking pipette, not graduated cylinder. But to make a solution, you need to know that you are using a volumetric flask. All right, so we're going to use a volumetric flask to make one. So these are pipettes. and you've seen me, I think, use them before, like when I'm adding nitric acid in the fume hood or something like that. I'm using pipettes with you. That's the volumetric flask. So we still, in general, the community of AP teachers still thinks that both of these questions you are going to have are going to be centered around a lab and lab data, with then additional questions beyond it. So there's every likelihood that they may have a picture of a lab setup. So these are good things to recognize. There may also have a description or be using terms. So if you see anything mentioned around a volumetric flask is specifically used to make a very specific molarity solution. All right, either a stock solution or doing a dilution. All right, volumetric flask are also really good for dilutions. So that's that stuff. There's Jackson. Okay. So this is, I think, a question, this type of question, I think, is a type of question that is certainly very reasonable now that they might actually throw on a free response question, whereas in the past, I think it was less likely. But describe how to prepare 250 milliliters of a 0.5 molar solution of sodium hydroxide, they've given you the molar mass, from solid sodium hydroxide pellets. So if they say describe how to prepare, and that is literally something that I had you doing before, but describe how to prepare means basically what mass all right, so what mass do you need of this stuff? What mass and what equipment? So go ahead and figure out what mass and we can figure out what equipment, what steps in the equipment we would need. So you should be able to use that molarity and volume to figure out your moles, and then use the molar mass to figure out the mass. Do we have a mass?
Is it 50,000?
50,000 grams?
That's what I got, but I don't know if I did something wrong.
Anybody else get 50,000?
No, is it, wait, is it 0.125?
So, Miss Baskin, what I did was I used the thing that you just gave us where you said moles equal molarity times liters.
Uh-huh.
And so I turned, oh, I went the wrong way.
Okay. So
Wait, did I? Because when you do for milliliters, I would go to the left or to the right to get liters. That's to the left?
to the left.
Okay, that's what I did. I went to the right. I went from like liters to milliliters, or I thought I went backward.
So once you do the 0.250 times 0.5, That's where you get
Yeah.
Cassidy's 0.125, and then you multiply it by the molar mass.
Yeah.
Yeah.
Okay.
Calculator is just so far away.
Well,
Yeah. So Cassidy, you did the first step, then you just got to multiply it by the molar mass.
Oh.
Okay. And then you got to remember, you are not actually adding that to 250 milliliters of water. You are trying to get 250 milliliters of solution. So you add enough water until you get to 250. And what piece of equipment would we be doing this inside?
a volumetric flask.
Yeah, volumetric flask. So make sure you know that there is no way, shape, or form that you would be doing this inside a beaker, inside a graduated cylinder, inside a Erlenmeyer flask, inside of anything other than a volumetric flask. Anything having anything to do with making a solution is going to be inside a volumetric flask. Okay. Okay. Next. All right, so what's the molarity of this thing? So a couple things to note. Number one, they gave you milligrams instead of grams.
Why?
So that, but regardless, molarity means you got to get the, you have to get this milligram amount to moles. And you got to get this milliliter amount to liters. And then calculate the molarity. Does this 25 milliliter sample part matter?
No.
Do you have to do any amount of conversion or calculation with that number?
No.
Mm-mm.
No, because any sample of this larger solution will have the same molarity. So just figure out, convert your milligrams to moles, your milliliters to liters, and figure out that molarity.
Wait, so I have a question.
Yes.
So we get the acid from milligrams to grams to moles.
Yes, ma'am.
And then how do we know how many moles to convert it to get to the other solution?
You don't have to. It's just that many moles
Mm-hmm.
divided by the volume to make the solution.
Okay.
I like that they give us the molar mass.
Yeah.
Was I supposed to do the 276, change that to liters too?
Change it to grams from milligrams, so it's like the same thing. Yeah, bump it
Well,
over.
yeah.
Yeah, 3 places left. Yep.
Oh.
So it should be a small molarity.
Mm-hmm.
Is that what you guys were getting?
Mhm.
Yeah, looks like it.
Yeah, 0.02.
Mhm.
All right, so this guy, it wants to know the concentration of a specific ion, and I'm mixing two things together. So you have to think from the calcium bromide, how many moles of bromide ion are there actually?
1, maybe.
So I have this much of the full sample, but of just the bromide, I have.
So 30 plus 25.
So it would be, for
Oh,
this
wait.
one, it would be the 0.30. And why is it 0.30 and not 0.15?
Because the
Because there are
subscript is
Two
2.
of them.
Yep.
Yay!
This guy makes me multiply. All right. And then that's how I got that number, the 0.30. But here it's just the 0.25. So adding those two together is correct. So that would give me the 0.55. And then if I want the molarity, right, boom, boom, boom. So 0.55 divided by 0.4 should give me a larger. All right. So if you took that 0.55 and divided it by 0.4, your calculator would give you 1.375, which is going to round to the 1.4.
Mhm.
Okay. So the only thing here I want to make sure is people understand what we did with the calcium bromide there.
Mhm.
Okay. Aha. Dilution. This is a formula that's not on your formula sheet that we're going to write down. What is the formula we are about to write down? What's the dilution formula?
Wait.
I'm not even gonna pretend that I know what it is.
What?
I don't remember.
If I write the first part of it?
Oh, M1.
M1V1
That's the
equals.
dilution formula? I
Oh.
knew that. I just didn't know it was called that.
Yep.
Yay.
M1V1 equals
M2V2.
M2V2. All right. So out of that, what information did they give me?
M1V1.
All right, they gave me M1 and V1. So I can call this M1. I can
And
call this V1. Do I need to change this out of milliliters?
No.
No. Okay. So what other thing did they give me?
V2. I mean M2. M2.
All right, they gave me M2.
Mhm.
So clearly what you're solving for
It's V2.
is V2. Now, be careful. Is the question asking you for V2 or asking you a question based on V2?
A question based on V2.
A question based on V2. Okay, so solve for V2 and then see if you can get what they are actually asking you for.
Okay, I have V2.
Okay, what are you getting?
375.
Okay. So based on the text of the question, what are they asking you to do with that number?
Subtract.
Subtract what?
That's what I am lost at.
Subtract that from the original 150.
Yup. Because it wants to know what volume of water would be needed. So this 375 is my total volume.
Oh, it's because it's the total. Oh, okay.
Okay. And they want to know how much water I add to the original 150 to get the 375.
Okay.
So what is that?
225.
Yeah. So 375 is my total. Oh, they did that wrong. Huh. Oh, well. We're right. It's 225. 225. Okay. Representing solutions. This is basically your particle diagrams. Can you count things in a picture?
No, I cannot.
Yes, you can.
Yes.
Yes, you can. The number of particles is our information. So when you're dealing with particle diagrams, there's a couple of things we need to remember. So number one, you got to remember charges matter. Pay attention to the charges on the particles. So, because most of the time, unless they specifically say otherwise, most of the time your solution will actually have a neutral charge. So you need to make sure that you have a balanced amount of positives and negatives. So charges matter. Sometimes that means the orientation of water molecules will matter, but we know since they are not asking you to draw stuff, that you're not actually going to have to draw out a particle diagram, which they have done in the past. The other thing to remember in a particle diagram, count the things. If they give you a particle diagram, then for whatever reason, the number of particles in there is fundamental to answer the question. So count the stuff. That is, those two things are the only reason they give you a particle diagram, is because of charges and because you have to count things to be able to answer the question. Hands down. That is nice, actually, because that makes your life a little easier, because those are easy things to do. It's easy to count the things. All right. So in this little thing, green particles are cations, purple particles are anions. Do I have a balance of charge?
Mm-hmm.
Yeah.
Yes.
Yes, because you count the things and there's an equal number.
Yes.
Okay. So it says the particles in the beaker represent a 1 molar solution of lithium fluoride. If another solution contains 12 green and 24 purples, so what's the difference in the ratio?
It's double.
It's
One to
double.
two.
Which is doubled?
One green to 2 purple.
Right. So your anion concentration is doubled. So what does, if this is our original formula, right? So if this is our original formula, 12 to 24 means which part of it is doubled?
Wait, we said the purple is okay.
The
So
F.
The F is going to be doubled. So you are looking for something that is double on that side. So could it be that one?
no.
Nope, because that's 1 to 1. Could it be that one?
No.
No, that would be 2 to 1. We're looking for a 1 to 2, which is why it's that one.
There it is. Wow.
Yay. Okay, so that's what I mean by you just have to be able to count stuff. Okay, so if you did have 12 to 24, this original one over here, what's the ratio between these things?
1 to 1.
Right, it's 1 to 1, so we have 6 to 6, right? But if we go to 12 to 24, what would you say about the concentration? Does it seem to be more, less, or the same?
More.
More.
More. It would definitely be more because 12 is definitely more than 6. Yeah.
Okay.
Okay. So the charge helps you figure out the ratio. All right. So that sort of thing, those things are related. And then the concentration is just the total number of particles that you're looking at. Okay. Chromatography technically is based around solutions. Do you remember the chromatography lab we did a very, very long time ago?
That the one with the colors?
Oh,
Yes.
yeah.
Yeah, then yeah.
Yay, the
Well,
colors.
not where we looked through the
First one that we did almost.
Yeah, it's the first major lab you did.
this year.
No, I'm a Marie.
No.
Okay.
Yeah, sophomore year.
Oh,
So
is this the where we looked through the thing with the colors in it.
no. This is
Okay.
the one where literally you had a piece of paper and you were dotting colors.
Okay.
Yeah. It was a very long time ago. I think this is an unlikely choice for a lab-based free response question, but we will go back over it regardless. So when you're talking about paper chromatography, we were talking about separating dyes and pigments. So we had the solute, which was basically for us the colored stuff. The solvent, which is what you dipped the paper in. And we had what we call the stationary phase, which was the paper. The mobile phase, which was the solvent, the stuff that would move. So when we did the lab, our solute was the different colors of food dye. The stationary phase was the actual strip of paper. And the mobile phase, we did two different ones. We did a salt solution and we did an alcohol solution. And this whole process works on basically figuring out, does the solute prefer the stationary phase or the mobile phase? And by prefer, meaning is it attracted to the mobile phase or the stationary phase? And that'll determine how much it moves. So if the solute, if our food dye was really attracted to the stationary phase, the paper, how much did that little dye dot move?
Barely any.
Barely any. But if it was really attracted to the mobile phase, then it basically ran off the paper. And we had some dyes that basically stayed down there at the bottom, and we had some that were literally at the front. So most of the time, if you do a chromatography experiment, you do it the way we did, where we had one mobile phase that was the salt solution that would be very, very polar, ionic polar. And then we had one that was basically the opposite, the alcohol, where you're going to have a different type of polarity. So you can also do it where you'd have a polar solvent and then something like acetone or something. They would tell you that it was a non-polar solvent so that you could see the difference in how that they would run, because very few things would run the same way in both. So that picture, hopefully that picture brings back some memories. And then I had you tracing things off with the ruler so that you could calculate the RF. All right, distance traveled by the substance over the distance traveled by the solvent. Is this all seeming a little more familiar?
It's getting there.
Okay, cool. All right, so basically all of that is saying what you guys just said, like it's obvious to think which one is thinking which. So to be able to answer questions about this, they have to tell you information about the polarity of the different substances involved. So they have to tell you about the polarity of the stationary phase. They may give you information about the mobile phase where you have to figure out the molarity, but you have to be told about the stationary phase because there's no assumption of what the stationary phase would be. So again, don't think this is super likely, so I don't want to worry about it too much. Yeah, markers, that's what people did. Yeah, like, you know, black ink is not actually black, it's a mixture of things. Cool. Okay. Distillation is not a technique that we actually did because we don't have a distillation tube of any sort, but it's another thing that allows you to separate different things in a solution. It is most useful when you are trying to separate two liquids. And those two liquids otherwise would not be easily separatable because they mix, but the only difference is they have different boiling points. Yeah, things with lower boiling points are going to come off first. Again, this is not a thing I think they're going to ask about because most people do not do a lab with distillation because it is not standard high school equipment. So ain't too worried about it. Yeah, duh. Okay. Don't care. Moving on. All right, so these two things. So first off, you look at structures. The very first thing you should do if they give you a larger structure is start thinking about what kind of intermolecular forces might be here. So if I look at these two structures, what kind of intermolecular forces might these two things have?
LDFs.
LDFs.
Hydrogen bonding.
They would have hydrogen bonds. Actually, no, they would not. There's no hydrogens attached to oxygens.
Oh.
So no hydrogen bonds, but they would have.
Yeah.
Dipoles.
They would have dipoles because the oxygens would create dipoles. So who's gonna have stronger intermolecular forces? The one on the left or the one on the right?
The one on the right.
The one on the right. Larger molecule, it's got more ability to stick together, right? More polarizable electrons over here for your LDFs. So, so if that's the case, who is going to evaporate first? The one on the left or the one on the right?
The one on the left.
The one on the left. All right, so this has weaker forces on the left, so it will evaporate first. Cool. All right, solubility. This involves intermolecular forces. So if things have similar attractions, similar forces, they will dissolve in each other, right? So that explains why our oil and water don't mix. Right, so polar will dissolve in polar, non-polar will dissolve in non-polar. That we all know. So I still think intermolecular forces are going to be a big thing on here because if they can't have you draw a structure and they can't test that sort of thing, they're going to basically have to ask you questions about structures. So I think it's highly likely that they're going to provide one of these two questions is going to have a couple of structures that you're then going to have to answer questions about hybridization, intermolecular forces, that sort of stuff. So we just need to keep practicing stuff like that. Which of the following would not be soluble in water? Well, that's polar, that's polar, that's non-polar, and that's polar. How can I very quickly tell that these three things were polar? Like, I don't have to draw those to know that those are polar.
Hydrogen.
Because the 3 with the odd number?
The odd number definitely helps. So for this first one, the odd number of 3 hydrogens lets you know that that must mean that the fourth thing on nitrogen is a lone pair. So that's one thing. These 3s are telling you, it's like, okay, so I've got 3 of the same thing on 3 of my sides of carbon, but my other thing is something totally different. So basically, you should be able to look at these 3 formulas and know that there is no way that those things are symmetrical. And if they're not symmetrical, then they're going to be polar. Whereas this, those all 4 the same thing, so it's symmetrical, it's non-polar. That's kind of the way you need to approach that sort of question. All right, so looking at these things, before even looking at the question, right, we're looking at the structure. Are any of these non-polar?
The last one?
No, it's the first.
The butane, and I think both the butane and the ethylene glycol are non-polar.
Oh, I'm thinking about polar with the non-symmetrical thing.
Right. So butane is definitely non-polar. Like there's nothing in there but carbons and hydrogens. And it's symmetrical, right? You can like cut this thing in half. So then as far as ethylene glycol goes, while it is symmetrical, it is also going to be polar because of all of these lone pairs on these oxygens. These can have dipole interactions. Just like this can have dipole interactions, and both of these can have hydrogen bonding, these OH groups, on both the ethylene glycol and the propanol. So who is the least soluble in water here?
Butane.
Butane. And who would be the most soluble?
The
Probably,
one on the right.
yeah, ethylene glycol.
It's the ethylene glycol. And you can basically imagine it's because it's got double of the, right? So the propanol has this OH. We recognize that as something that makes it polar. Ethylene glycol has two OHs. So it's twice as polar is how to think of it. Does that make sense? Maybe?
Yes.
Okay. Okay. We do not care about topic 3.11. We don't. This is a new topic and everybody's like, yeah, you're not asking a question about that. It's stupid. Photoelectric effect, we covered this with atomic stuff, right? Like we did a problem with these using those equations on your sheet. So I don't know why. This is one of the things that we assume is in unit 1, but they weirdly put it in unit 3. So, okay, awkward, strange, right? We know this diagram. We've calculated, we did those practice calculations. We've done a question like this. Moving on. All right, so the last thing that actually makes sense is Beer-Lambert law. And while we haven't been specifically using this term, this is what dictates spectroscopy, using the spectrophotometers to measure the concentration of solutions. That's what this is. That is a lab technique that we used at least 3 or 4 times. That equation is on your formula sheet. I don't remember where it is on your formula sheet, but it is. Beer-Lambert law, if I remember correctly. I could be wrong, but I think it's on there somewhere. Yes, on gases, liquids, and solutions. You should have a formula, the last one, that says A equals ABC.
Yeah, I see that.
And then they've defined A and ABC on the right. We did a couple of questions on labs that use that formula, but basically this is what allows us to use a spectrophotometer to figure out concentration when we have absorbance, which is why we used that piece of equipment specifically, because it allows us to do that. So remember, how are those two things related? Absorbance and concentration. A higher absorbance means what for concentration?
Less concentration. Or no, more concentration.
More concentration, right? Absorbance means how much of the light is going to get absorbed and not pass through the solution. So the more concentrated your solution, right, the more light it absorbs and less passes through. Right? So, and we almost exclusively did this with the blue solutions, right? We did it with blue food dye, we did it with blue copper, and then we also did it with the purple stuff and whatever. So I don't think that they would ask you to use the specific little, that actual formula to do a calculation, because that's kind of like a basic thing. I think it is more likely that this is something that they could use. Do you remember making those? Because I made you do it by hand.
Yes, I do.
You're like, yes. So notice your Y and your X axes, they can very easily, right? We're going to love it if they put a graph question on, because a graph question means like you just have to have graph reading skills, right? So you've got absorbance on your Y, you've got concentration on your X. This is a, this is basically like a calibration curve that allows you, right? So we did one of these, we made dilution series and made one of these graphs, and then you took some random sample, we stuck it in the spectrophotometer, we got an absorbance value, and then you traced a line over and said, okay, so it has an absorbance of 0.75, and so we drew it over here and said, okay, so what does that mean for the concentration? And we said, oh, so our sample based on this graph had a thing like this. That is how we used this graph. So, and that's exactly what they asked you to do. So if the absorbance of the mixture is 0.9 at 453 nanometers, which doesn't matter, that number doesn't matter. How many moles of iron were present in a 100 milliliter sample? So they're asking you to actually do two things. One is read the concentration off, and then two, use that concentration and this volume to get moles. All right, so they're saying, so we would estimate that my volume, or that my concentration is that. And if I have a 0.1 milliliter or a 100 milliliter sample, 1, 2, 3, so that's 0.1 liters. So you are simply multiplying those two things together. And you would get that. That's how we use this. And that's it. That's the slide deck. That's unit 3. Way. Woo. Okay. So, term 4. Did my email make sense?
Kind of.
Kind of.
Because like, okay, so term 3, we were only supposed to be getting quote unquote extra credit. But then you said for term 4, like something about like our grade being neutral. So like, isn't that essentially the same thing? Our grade doesn't really get bad.
So there's a difference. Your overall course grade cannot get bad, but you will actually have a term 4 grade that right now does not exist because we don't have any assignments.
Oh, okay.
So the difference is your term 4 grade can't bring your overall grade down.
Which means that this is redundant.
Well, it is, but for the most part, I don't know about your other AP classes, but for me, term 4, because the AP exam has always fallen so soon into term 4. Term 4 for me has always been in my AP Chem class, you should get an A because I'm not going to give you much stuff. So basically for us, we have 3 weeks until the exam. So we have 3 weeks of doing some adding shit on collaborative notes and doing personal progress checks. And that's going to be your term 4 grade. Like, I'm not making up extra shit after this. Like, I'm not, because I have enough other things to do. And so it should be easy for you to get an A. So most people's grades, term 4 ends up pulling their grades up.
Okay,
That's kind of always been my intention with how I set up AP chemistry in term 4 anyway.
But like, you're the only teacher who like has common sense.
Common sense.
Are you still recording? Oh my god.
Oh,